Okay, hi folks, and welcome to another walkthrough of an SQA Higher Physics multiple choice paper, and this time it's the turn of the 2024 paper, which has now been published on the SQA website, and you'll also get it on the Calderglen High School Physics website. Just go to the Higher Physics page and scroll down and click on Higher Physics SQA past papers, and it's the first one in the table there. You'll get paper 1, paper 2 and all the answers as well, but we're going to click on 2024 paper 1, and there it is. It's a 45-minute paper and there's 25 marks, and we're going to try and do this in about half an hour. And as usual, first thing you see in the paper is the datasheet that contains the numbers that you might need as you work through the paper, and it is suggested that you pause this video, work through the questions yourself first, and then come back when you're ready and we will show you how we have done it. So, question 1. A cyclist travelling along a straight track accelerates at 1.2 metres per second squared, and the speed of the cyclist increases from 4 metres per second to 7.5 metres per second, and we've to work out the distance travelled by the cyclist during this acceleration. Well, this is a SUVAT question, or TUVAS, or whatever acronym you use to remember the 5 different variables in the equations of motion. So let's write them down first. S, U, V, A, T, and what they're equal to. So the acceleration was 1.2 metres per second squared. The initial speed U was 4 metres per second. Final speed 7.5 metres per second. And we're interested in the displacement, or the distance gone, so we don't need the time. So the relationship we're going to use that doesn't have time in it is v squared equals u squared plus 2as. Then let's sub in our values from our little list on the left hand side there. So 7.5 squared is equal to 4 squared plus 2 times the acceleration, which was 1.2, times s. Now we can rearrange this. We could do 7.5 squared minus 4 squared is going to be equal to 2.4 times s, and then work out what the left hand side there is. That's going to be 40.25, and then if we divide both sides by 2.4, that'll leave us with s on the right hand side there, which works out to be 16.77 metres, which rounds to 17 metres. That's answer B. Moving on, question 2. It says a ball is thrown vertically upwards and returns to its original position, neglecting air resistance. Which displacement time graph represents its motion? Well, if the ball is thrown vertically upwards, then it's going to move away from its initial starting point, and its displacement is going to increase at a decreasing rate because it's going to decelerate upwards. Then it's going to stop at its maximum height, and then it's going to accelerate downwards, so that displacement is then going to reduce at an increasing rate on the way back down again. So there's the displacement increasing at a decreasing rate, and there it is decreasing at an increasing rate back to its starting point. This is a bit like the path of a projectile, but we're only looking at the vertical displacement over a period of time. That's pretty tricky for question 2. That's question 2A. Okay, moving on. Question 3. A box is suspended from a ceiling by a rope. A horizontal force is acting on the box to the right, and the box is held stationary as shown. The weight of the box is 4.9 newtons, and we've to work out the tension in the rope. So easiest thing to do here, draw a right angle triangle, and the hypotenuse of that triangle will be the tension. The vertical side of the triangle will be equal to the weight of the object, because it will be equal to the reaction force acting in the opposite direction to the weight. And if we draw a little dotted line, then that angle in there is 20, and by z angles, that little angle's 20 as well, and then we can use the cos of that angle. Remember, cos 20 will be equal to the adjacent over the hypotenuse, so that'll be 4.9 over the tension, and then rearrange that for the tension. So the tension will be 4.9 divided by cos 20, and if you do that on your calculator, you get an answer of 5.2 newtons. That corresponds to answer D. That's 3D. Question 4. A ball is thrown horizontally over the edge of a cliff. A group of students draw 3 velocity time graphs to represent the motion of the ball when air resistance is taken into account. And then we have to state which row in the table shows the graphs that represent the horizontal component of the velocity and the vertical component of the velocity. Well, if there was no air resistance, the horizontal component of velocity would be a straight horizontal line. But because there is air resistance, then that horizontal line dips down as that velocity decreases due to the effects of air resistance. So graph X is going to be our horizontal component of velocity. Now, what about the vertical component of velocity? Well, if there's no air resistance, it should be a straight line through the origin because it's got a constant acceleration downwards. And when air resistance is taken into account, then the gradient of that graph is going to decrease. That's the same as you saw with your terminal velocity graphs in National 5. So graph Y is going to be our vertical component of the velocity. Now let's have a little look at the options we've got and the answers. So graph X is the horizontal component and graph Y is the vertical component. That's answer A. Question 5. In a hydroelectric power station, water flows from a reservoir through turbines at a rate of 4.5 times 10 to the 6 kilograms per minute, and the reservoir is 150 metres above the turbines. And we have to work out the total power delivered by the water in falling from the reservoir to the turbines. So this is power and potential energy. So let's start off with our power relationship. Power is equal to energy over time. And the energy delivered will be the loss in the gravitational potential energy of the water. So that's mgh divided by the time. So let's sub in the values that we know. The mass was 4.5 times 10 to the 6. G on Earth is 9.8 and the height was 150 metres. And that's divided by, well, the time is per minute. So we're going to put 60 seconds in there. And then if you do that correctly on your calculator, you'll get an answer of 1.1 times 10 to the 8 watts. And that corresponds to answer C. That's 5C. Question 6. 2 trolleys move along a level bench as shown, and the trolleys collide and stick together, and they continue to move along the bench. And we have to work out the velocity of the trolleys immediately after the collision. So this is conservation of momentum. So the total momentum before the collision will be equal to the total momentum after the collision. Momentum is mass times velocity, and because we've got 2 vehicles moving before the collision, we can write that as m1u1 plus mu2u. That's the mass times the initial velocity of the vehicles added together to give us the total momentum before the collision. Afterwards they stick together, so we've got a new mass m3 times a new final velocity v3, and then we can sub in everything we know. For vehicle 1, its mass was 2 kilograms times its velocity was 5 meters per second, and for vehicle number 2, its mass was 6 kilograms times its velocity of 1 meter per second, and that gives us a total momentum before the collision of 16 kilogram meters per second. And then on the right hand side, we've got m3, which is the 2 masses added together when they stick together. That will be 8 times the new velocity v3, and that means v3 is going to work out at 2 meters per second, and that corresponds to answer C. Okay, moving on. Question 7. A spacecraft is travelling at a speed of 0.2 c, that's 0.2 times the speed of light, relative to the Earth. And the spacecraft emits a signal for 20 seconds as measured in the frame of reference of the spacecraft. So an observer on the Earth will measure the duration of the signal as... Well, this is a special relativity question and a bit of a tricky relationship, so the best thing to do here is to go to our relationship sheet. Just check that we write it down correctly. And again, if you don't have one, you'll find one on the Higher Physics page of the Calder Glen High School website, and under Useful Documents there is the relationship sheet. And the relationship sheet is laid out in the order of the unit. So Unit 1, our dynamic universe, all those relationships are on the left hand column. And there's the one we're looking for. It's the time dilation relationship. So let's copy that down. T dashed equals T over the square root of 1 minus V over C squared. And then we're going to substitute in everything we know from the question. So the time for the emitted signal was 20 seconds, and that's divided by the square root of 1 minus 0.2 C over C all squared. Now those C's will cancel out, so that's going to simplify to T dashed equals 20 over the square root of 1 minus 0.2 squared. And then if you do all of that on your calculator correctly, it gives you an answer of 20.4 seconds, which corresponds to answer D at 7D. Question 8. Also in special relativity, the Queensferry crossing has a length of 2,700 metres as measured by a stationary observer on Earth. And a spaceship travels past Earth at a constant speed of 1.8 times 10 to the 8 metres per second relative to Earth. Then we have to work out the length of the Queensferry crossing as measured by an observer on this spaceship. So back to our relationship sheet again, and this time it is the length contraction relationship we're looking for. And then make sure we copy that down correctly onto the question paper. L dashed equals L times square root of 1 minus V over C squared. Again, sub in what we know. So the proper length is 2,700 metres times 1 minus, now we have to put in the actual velocity here, 1.8 times 10 to the 8 divided by the speed of light, which on your data sheet is 3 times 10 to the 8. And then don't forget to square V over C. And again, doing all that correctly on your calculator will give you a shortened observed length of 2,160 metres. But all the numbers in the question are to two significant figures, so we round that answer to two significant figures, and we get an answer of 2,200 metres. That corresponds to answer C. Question 9. The graph shows how the energy emitted per second per unit area varies with the wavelength of the radiation for stars W, X, Y and Z. And this diagram has appeared in most National 5 and higher papers over the past 8 years or so, and it gives us an indication of how the peak wavelength emitted by stars of different temperatures shifts towards the shorter wavelengths as we go from lower energy to higher energy output stars. So let's have a look at the three statements and decide which of them is or are correct. So first one, star Z is hotter than star W. Well, yes it is, because the peak of star Z is higher than star W, so it's emitting more energy per second, it's more powerful, so it's hotter. Statement 2, the peak frequency of radiation emitted is greatest for star W. Well, if we look at the x-axis here, it's wavelength, and wavelength is increasing as we move to the right there. And so star W, the peak of star W, is longer than all the other stars. And so therefore, as we go to the left, then the wavelength is getting shorter, so we've got an increasing frequency. So star Z has got the highest peak frequency, which means that statement 2 is incorrect. And then statement 3, star Y emits more energy per second per unit area than star X. Yes it does, because it's got a higher peak. So statements 1 and 3 are correct. That corresponds to answer D, that's 9D. Right, moving on, question 10, this is the start of the particles and waves questions. And we're asked, which of the following particles is a fermion? Well, it would help here if we could have a look at the table of fundamental particles from the Standard Model. And here it's here, so you should be familiar with these 16 elementary particles. The green and blue ones on that diagram are the fermions, that's the quarks and leptons. And the kind of pinky red ones are the bosons, that's the force mediating particles. So let's have a look at the answers one at a time. So the W and the Z boson, they're obviously both bosons. So is the photon, so is the gluon. That only leaves us with the muon. It's a fermion. And therefore the answer to question 10, which of the following particles is a fermion? It's the muon. That's answer E. Got to know your fundamental particles. Question 11. The following statement represents beta decay, and you may well remember from your National 5 work that beta decay is the emission of a fast-moving electron. And in this example, we've got a neutron, which is changing into a proton, with the emission of the fast-moving electron, and this little thing here. Well, that little thing there is a neutrino. It's actually an anti-neutrino, but that's a story for another day. But beta decay provided the first evidence for the existence of neutrinos. Question 12. Uranium-239 undergoes decay by emitting a beta particle, and the nucleus formed as a result of this decay also undergoes decay by emitting a beta particle to form nucleus X. And we have to identify what nucleus X is. So if we start off with our uranium-239 nucleus, then what is going to be formed when this emits two beta particles? So it will give out the first beta particle and turn into some new element, and then give out the second beta particle, and we end up with nucleus X that we're looking for. So let's think about the first stage of that. Let's call it nucleus W. This is very similar to the previous question, that when a neutron turns into a proton, then a beta particle is given out. And so the atomic number, the bottom number, is going to go up by 1, because a neutron turns into a proton, and the top number isn't going to change. And then when our second beta particle is given out, that bottom number goes up by 1 again, top number stays the same, and we get nucleus X, which is what we're looking for. Remember, a beta particle has got negligible mass, a charge of -1, and hence if you take away -1, then your atomic number goes up by 1. So if we're looking for an element that's got an atomic number of 94, we really need a periodic table here to identify that element. You'll find a periodic table at the back of your relationship sheet, or again, if you're looking for one, we've got one on our website under Useful Documents, and you can either click on the relationship sheet or the periodic table. I'm going to go to the relationship sheet, scroll right to the back of it, and there's your periodic table. Now, let me rotate that, and I'm only interested in the little section that's got uranium in it. So there it's there, uranium's number 92, and when it gives out the first beta particle it becomes neptunium, and then it gives out the second beta particle and becomes plutonium. I'm just going to copy that wee section onto the question. There we go, uranium, neptunium, plutonium is number 94, so our answer to question 12 is 12E. Moving on, question 13, still with nuclear reactions. The following statement represents a nuclear reaction. We've got a carbon nucleus fusing with a helium nucleus to become an oxygen nucleus, plus a gamma photon given out. This is maybe taking place in a very dense star or in a supernova. And we're told the mass of the particles before the reaction and the total mass of the particles after the reaction. And the mass afterwards is less. And we have to work out the energy released in this reaction due to that lost mass. Well, we can work out the lost mass by finding the difference between those two numbers. And if you do that in your calculator, you'll get an answer of 1.2 times 10 to the minus 29 kilograms. If we then substitute that into the relationship E equals mc squared, you'll get 1.2 times 10 to the minus 29 times 3 times 10 to the 8 squared. And if you do that correctly on your calculator, it gives you an answer of 1.08 times 10 to the minus 12 joules. And that corresponds to answer D. That's 13D. That's quite a lot of questions about nuclear reactions in the multiple choice. Anyway, on to question 14. This is about irradiance. A student carries out an experiment to investigate how irradiance of light varies with distance. A small lamp is placed at a distance d from a light meter, and the irradiance at this distance is displayed on the light meter. And this measurement is repeated for a range of different distances, and the student uses these results to plot the graph shown below. So there it's there, they plotted a graph of I against 1 over the distance squared. But the graph doesn't go through the origin. So if we were to plot the student's points, the line should go through the origin. So the graph indicates that there's a systematic uncertainty in the experiment. So which of the following alterations would be most likely to reduce this systematic uncertainty in this experiment? Well, all the irradiance values are too high. The line has been shifted up, if you like, up the y-axis. So there's probably some background light in the room, and the way to reduce that is to repeat the experiment in a darkened room. That's 14A. Question 15. A group of students make the following statements about coherent waves. Well, coherent waves are identical. So statement 1 is correct. They have a constant phase relationship. They will have the same frequency and the same speed. All three statements are correct. That's 15E. Question 16. Dark lines in an absorption spectrum occur because, well, an absorption spectrum is what you get when you shine pure white light through an unexcited element like a gas, and there are black lines in that spectrum because electrons in the gas or in the unexcited element have been excited from a lower to a higher energy level by absorbing some of the photons from the pure white light. So that's 16E. Question 17. A ray of monochromatic light passes from air into diamond. The frequency of the light is 5.09 times 10 to the 14 Hertz. So what's the speed of the light in the diamond? Well, to do this, we need the refractive index of diamond, which you get on the data sheet. There it's there. Diamond is 2.42. And then let's write down the appropriate relationship for refractive index. Now we only need the bit of the refractive index relationship that's got velocity in it. So n equals the velocity of light in air divided by the velocity of light in, well, in this case in the diamond. I usually use a G for glass there. Let's sub in the numbers. So 2.42 was the refractive index of diamond. The speed of light in air is 3 times 10 to the 8. And that will be divided by the speed of light in the diamond. Let's rearrange that then. So Vg will be equal to 3 times 10 to the 8 divided by 2.42. And if you do that on your calculator, it gives you an answer of 1.24 times 10 to the 8 meters per second. And that corresponds to answer C. That's 17C. That's the last of the questions from particles and waves. We're now on the home straight. This is electricity. So question 18, a circuit is set up as shown. It's a mixed series and parallel circuit, and the power supply has negligible internal resistance. And we have to work out the potential difference, that's the voltage, across the 60 ohm resistor. Well, let's do a little bit of National 5 physics first and work out the total resistance of the 30 and the 20 ohm resistor in parallel. That gives you 12 ohms. I can then redraw a simplified version of the circuit diagram, and we've got our 12 ohm resistor in series with the 60 ohm resistor. And these two resistors are sharing the 12 volt supply. So we'll have some of the voltage here, some of the voltage here. We're looking for V2, the voltage across the 60 ohm resistor. And again, using our National 5 relationship, V2 equals R2 over R1 plus R2 times the supply voltage. Sub everything in, gives us an answer of 10 volts. And that corresponds to answer E. You could also have done that by ratios, because the ratio of 12 to 60 is 1 to 5. And so those two voltages then will be 2 and 10, so that they both add up to 12. And so V2 is equal to 10 volts. That's 18E. Question 19. A resistor of resistance 2.2 kilo ohms is rated at 0.25 watts. And we have to work out the potential difference, that's the voltage across the resistor, when it's operating at its rated power. So we need a relationship here that's got power, resistance and voltage in it. And we're going to use P equals V squared over R. It's V we're looking for. So let's rearrange it. V squared equals P times R. That's 0.25 times 2.2 times 10 to the 3. If you do that in your calculator, you get an answer of 550, but that's V squared. So don't forget to square root it. And when you square root it, you get an answer of 23.45 volts, which rounds down to 23. That's 19B. Question 20. This looks like internal resistance. Whenever you see a dotted box around a cell or a battery, you know it's an internal resistance question. So the resistance of the variable resistor is changed, and the corresponding readings on the ammeter and voltmeter are used to produce the graph shown below. And that graph has got the terminal potential difference, the TPD, on the y-axis and the current on the x-axis. But the line hasn't been extended to the y-axis or the x-axis. So what I'm going to do first is I'm going to extend that line so that it cuts the y and the x-axis. Because where it cuts the y-axis is the EMF. So that EMF is greater than 12 volts. So statement 1 there says the EMF of the battery is 12 volts is incorrect. The EMF is going to be greater than 12 volts. Statement 2 says the internal resistance of the battery is 10 ohms. Well, you can work out the internal resistance of the battery by working out the gradient of the graph. And we can use the numbers that are on the x and y axis and use those coordinates in our gradient equation. So y2 minus y1 over x2 minus x1 will be 12 minus 2 over 1.2 minus 0.2. Do that in your calculator, gives you an answer of 10 ohms. So the internal resistance is 10 ohms. Statement 2 is correct. Statement 3, the short circuit current is 1.2 amps. No, it's not. The short circuit current is where the line crosses the x-axis and it's cutting the x-axis at a value greater than 1.2. So statement 3 is incorrect. That means only statement 2 is correct. That's answer B. Question 21. A capacitor is initially uncharged. It's now charged for 20 seconds using a supply that provides a constant current of 0.1 milliamps. The potential difference across the capacitor is now 12 volts. And we have to work out the energy stored on the capacitor. Well, before we work out the energy, we need to work out how much charge is stored on the capacitor using Q equals I times T. That's 0.1 times 10 to the minus 3 times the 20 seconds. Gives us an answer of 2 times 10 to the minus 3 coulombs. We can then use that in our energy equation. E equals a half QV. Then substitute in, the charge was 2 times 10 to the minus 3. The voltage was 12 volts. Do that correctly on your calculator. Gives you an answer of 0.012 joules. That's 12 millijoules. Corresponds to answer B. That's 21B. Moving on then. Question 22. A circuit is set up as shown. We've got a capacitor in series with a resistor and an ammeter and a switch and a 12 volt supply. The capacitor is initially uncharged. The switch is now closed and the capacitor charges. And the graph shows how the charging current I in the circuit varies with time. So the initial current is 30 milliamps. That depends on the size of the resistor. And the capacitor is fully charged at 50 milliseconds. Then the capacitor is now replaced with an uncharged capacitor of a greater capacitance. So in other words, the resistance is unchanged. So the initial current is going to be unchanged. And the same charging process is repeated with this capacitor. So which graph shows us how the current I varies with time as this capacitor charges? It's a bigger capacitor, but the initial current is going to be the same because the resistor is the same. So the initial current's 30 milliamps, but it's going to take a greater time to fully charge because it's a bigger capacitor. So that's answer C, 22C. Question 23. Solids can be categorized as conductors, insulators and semiconductors, and the diagrams below show the valence band and conduction bands of three solids X, Y and Z, and we are asked which row in the table shows the letters that represent a conductor, an insulator and a semiconductor. Well, you should know that in a conductor the conduction band and the valence band are overlapping so that there's always electrons in the conduction band. In an insulator there's a large band gap between the conduction band and the valence band, so it's very difficult to move electrons from the valence band into the conduction band. But in a semiconductor, there's only a small band gap. So, Solid X is a conductor, solid Y is a semiconductor, and solid Z is an insulator. And the only row with all three highlighted there is row D. That's 23D. Question 24. An increase in the temperature of a semiconductor, well, if you heat it up, it's going to conduct better, its resistance is going to go down, so it will increase its conductivity by allowing more electrons to reach the conduction band. That's answer A. Watch out for answer B though, it says increase its conductivity by increasing the band gap. No, it won't, it'll decrease the band gap. That's quite tricky. Anyway, last question. Question 25 about LEDs in an AC circuit. A student connects 4 identical red light-emitting diodes to a 2-volt RMS AC supply as shown. Which of the LEDs, P, Q, R and S, will emit light? Well, it's an AC supply, which means it's changing direction. So LED P will conduct for 1 half cycle. LED Q will conduct for the other half cycle, and LEDs R and S are facing in opposite directions, so no conduction can take place. So therefore the only LEDs that will emit light are P and Q only. That's 25C. That's the 2024 multiple choice paper. Pretty tricky, a lot of reading in it. That's really quite difficult. Pretty tricky. Anyway, I hope paper 2 was a bit more straightforward. Don't forget the full finalised marking instructions are on the SQA website or the Calder Glen High School Physics website. But that's it for this video. Hopefully that was helpful to you. We'll see you in the next one.